The enzyme horseradish peroxidase, found in the roots of horseradish, is used extensively in biochemistry applications primarily for its ability to amplify a weak signal and increase detectability of a target molecule. It is a metalloenzyme with many isoforms and the most studied type is C. Structure. The structure of the enzyme was first solved by X-ray crystallography in 1997 and has been solved several times with various substrates. It is an all-alpha helical protein which binds heme as a cofactor. Substrates, alone, the HRP enzyme, or conjugates thereof, is of little value. Its presence must be made visible using a substrate that, when oxidized by HRP using hydrogen peroxide as the oxidizing agent, yields a characteristic change that is detectable by spectrophotometric methods. Numerous substrates for the horseradish peroxidase enzyme have been described and commercialized to exploit the desirable features of HRP. These substrates fall into several distinct categories. HRP catalyzes the conversion of chromogenic substrates into colored products, and produces light when acting on chemiluminescent substrates. Applications: horseradish peroxidase is a 44,173.9 Dalton glycoprotein with 6 lysine residues which can be conjugated to a labeled molecule. It produces a colored, fluorometric, or luminescent derivative of the labeled molecule when incubated with a proper substrate, allowing it to be detected and quantified. HRP is often used in conjugates to determine the presence of a molecular target. For example, an antibody conjugated to HRP may be used to detect a small amount of a specific protein in a Western blot. Here, the antibody provides the specificity to locate the protein of interest, and the HRP enzyme, in the presence of a substrate, produces a detectable signal. Horseradish peroxidase is also commonly used in techniques such as ELISA and immunohistochemistry due to its monomeric nature and the ease with which it produces colored products. Peroxidase, a heme-containing oxide or ductase, is a commercially important enzyme which catalyzes the reductive cleavage of hydrogen peroxide by an electron donor. Horseradish peroxidase is ideal in many respects for these applications because it is smaller, more stable, and less expensive than other popular alternatives such as alkaline phosphatase. It also has a high turnover rate that allows generation of strong signals in a relatively short time span. Moreover, in recent years the technique of marking neurons with the enzyme horseradish peroxidase has become a major tool. In its brief history, this method has probably been used by more neurobiologists than have used the Golgi stain since its discovery in 1870. Enhanced chemiluminescence. Horseradish peroxidase catalyzes the oxidation of luminol to 3-amine phthalate via several intermediates. The reaction is accompanied by emission of low-intensity light at 428 nm. However, in the presence of certain chemicals, the light emitted is enhanced up to 1000-fold, making the light easier to detect and increasing the sensitivity of the reaction. The enhancement of light emission is called enhanced chemiluminescence. Several enhancers can be used, but the most effective are modified phenols, especially p-iodophenol. The intensity of light is a measure of the number of enzyme molecules reacting and thus of the amount of hybrid. ECL is simple to set up and is sensitive, detecting about 0.5 pg nucleic acid in southern blots and in northern blots. Detection by chemiluminescent substrates has several advantages over chromogenic substrates. The sensitivity is 10 to 100-fold greater, and quantifying of light emission is possible over a wide dynamic range, whereas that for colored precipitates is much more limited, about 1 order of magnitude less. Stripping filters are much easier when chemiluminescent substrates are used. References. External links: Horseradish peroxidase at the U.S. National Library of Medicine. Medical subject headings.